Hey everyone, welcome back for another deep dive. We're about to unpack something pretty fundamental in machine learning. You ready to tackle gradient descent?
Always ready to dive in. It's one of those core concepts that really unlocks a lot of machine learning.
Absolutely. And we're working with some text excerpts you sent over, right? To kind of guide our conversation.
Yeah, that's right. Let's see what we can uncover.
Okay, so imagine you're a hiker trying to get to the bottom of a mountain. That's the analogy we're going with for gradient descent, right? It's all about finding that lowest point.
Yeah, it's a really good way to visualize it. In machine learning, that lowest point is what we call the minimum of a function. That function usually represents the error of our model. So the lower we get, the less error our model has.
Okay, so less error equals better predictions, right? 'Cause ultimately, that's what we want from our models.
Exactly. Think of it like trying to make the perfect cup of coffee. Too much coffee, it's bitter. Too little, and it's weak. Gradient descent is like fine-tuning that coffee machine to hit that sweet spot.
I like that. I need that perfect cup of coffee. So how does gradient descent actually, work?
Well, it starts with a random set of parameters. That's like the hiker starting at a random spot on the mountain.
So they're not just starting at the top and walking down.
Right. It's more like starting somewhere on the side and trying to find their way down.
Makes sense. So what happens next?
Okay, so then the algorithm calculates the gradient. You can think of the gradient as like a signpost that points uphill.
So it's telling you which way not to go, kind of.
Yeah, exactly. It's saying, hey, if you go this way, you're going to go up, not down.
So then what? The algorithm just goes the opposite way?
Exactly. It takes a step in the opposite direction of that gradient.
Okay, and is that step like a big leap or a small step?
Ah, good question. That's determined by something called the learning rate, which we can represent with the Greek letter alpha.
Ah, getting a little mathy here.
Just a touch. The learning rate, or alpha, basically controls how big of a step the algorithm takes.
So small learning rate, small steps.
Yeah, like the hiker's being super cautious, taking it slow. Large learning rate is like taking bigger strides.
But they might overshoot the lowest point if they're going too fast, right?
Exactly. It's a trade-off. Faster learning can be good, but sometimes those smaller steps are necessary to be really precise.
Gotcha. Okay, so we've got our hiker, we've got them taking steps. How do they know when they've reached the bottom?
Well, that's where something called the loss function comes in. This is basically how we measure how far the hiker is from the bottom or how much error our model still has.
So the loss function is like a measuring stick for how bad our predictions are.
Yeah, you could think of it that way. And so the algorithm just keeps taking these steps, calculating the gradient, checking the loss function, and it keeps going until it finds that minimum value of the loss function.
I see. It's like constantly checking their altitude and making adjustments until they're at the lowest point.
Exactly. Now, did you know there are different types of gradient descent?
Oh, I was just about to ask about that. You mentioned different ways to get down the mountain, right?
Right. Let's think about it like baking cookies. Batch gradient descent is like checking if the entire batch of cookies is baked before you take them out. You look at all the data, every single cookie, before you make a decision.
Okay, very thorough, but probably takes a while,
Yeah.
especially if you have a lot of cookies or data, I guess.
Uh-huh, exactly. That's batch gradient descent, thorough but potentially slow. Then you have stochastic gradient descent, which is more like tasting just one cookie to get a sense of whether the batch is ready.
So much faster, but maybe not as accurate because one cookie might not represent the whole batch.
Right, it can be a bit more unpredictable. It's faster but can jump around a bit more before finding that lowest point.
Makes sense. And I bet there's an in-between option too, right?
You know it. It's called mini batch gradient descent. It's like checking a handful of cookies from a couple of different baking sheets. A good balance between speed and accuracy.
I love these analogies. So where does gradient descent actually show up in, like, real-world machine learning?
Oh, it's everywhere. Think of something like linear regression, trying to find the best fit line to represent data, like predicting house prices based on their size.
That's using gradient descent behind the scenes.
Or you bet. It's finding that line that minimizes the error between the predictions and the actual house prices.
Cool. What about neural networks? They're kind of the rock stars of machine learning these days, right?
They are. And guess what? They rely on gradient descent for training. It helps adjust all those weights and biases, which are like the
Oh,
connections between the neurons, to improve the network's performance.
wow. So it's really behind a lot of the cool stuff happening in AI. But I'm curious, you mentioned earlier that gradient descent can sometimes get stuck.
Right? Yeah, that's one of its limitations. It can fall into something called a local minimum. which is like finding a small valley on the mountain that isn't actually the lowest point.
So it thinks it's reached the bottom, but it hasn't really.
Right. There are ways to work around this, like using momentum or adaptive learning rates. Think of it like giving the hikers some tools to help them explore more of the mountain.
So even with those potential pitfalls, it's still super useful.
Oh, yeah. Its simplicity, its effectiveness, it's a really powerful tool.
So any final words of wisdom for our listener about gradient descent before we wrap up?
Thinking back to that hiker, remember that the path they're walking on is really important.
What do you mean by that?
Well, in machine learning, that path represents the data that we're training our model with. Gradient descent needs good, clean, well-prepared data to work effectively.
So garbage in, garbage out, as they say.
Exactly.
Okay, I think we've covered a lot of ground today. We talked about how gradient descent works, the different types, how it's used in real-world applications, and some of its limitations.
We did. It's a really fascinating algorithm.
Absolutely. But here's a question for you and for our listener to think about. You mentioned that gradient descent can sometimes settle for those local minima, right? So as we develop even more complex machine learning models, how do we make sure that we're truly finding the absolute best solution, not just getting stuck in a valley when there might be an even lower point out there?
That's a great question to ponder. There's a whole world of optimization techniques out there beyond just gradient descent, and as the field evolves, finding those best solutions is going to be crucial.
That's an excellent point to leave our listeners with. Thanks for joining us on this deep dive into gradient descent. Until next time.